Unit 10, Nuclear Chemistry. I'm your instructor, Dr. Marc Taylor. In this unit, we're going to be talking about radioactivity. We're going to look at a periodic table. And while there are radioactive isotopes of every single element on the periodic table, some of those are naturally occurring, some of those are man-made, there are some elements on the periodic table for which every isotope of that element is known to be radioactive, and we'll look briefly at those. We'll talk about the types of particles that are released from radioactive elements. There are many different types of particles. We'll focus on three of them, the alpha, beta, and gamma particles. We'll talk about nuclear equations. This is an example of one shown here. Nuclear equations are similar to chemical equations, but now we are only focusing on the nucleus of atoms and how those nuclei change during a nuclear reaction. We'll also be talking about monitoring and measuring radioactivity, and that will lead us to looking at the half-life of radioisotopes. The half-life is the length of time it takes for half of that material to decay through its radioactive decay release of radioactive particles. We'll talk about exposure, health, and safety when working with radioactive materials. We'll talk about the medical and scientific applications of these materials. And finally, we'll conclude with nuclear power, which comes in two main varieties, fission and fusion. We'll talk about the differences and similarities of these two sources of enormous power. So radioactivity. Well, much of our understanding of the atomic structure came from studying radioactive elements, especially in the late 1800s and early 1900s. Radioactivity is the process by which atoms spontaneously emit high-energy particles, or rays, from their nucleus. Rays would be just energy itself. Particles, there would actually be matter associated with that release of radioactivity. So nuclear chemistry, the word nuclear comes from the fact that this is the chemistry of the atom's nucleus, as opposed to looking at the electron cloud of the atom and how it interacts with other atoms. That would be more of our standard chemical reactions. Nuclear chemistry focuses on the nucleus and how it can change. So radioactive decay will lead to a new type of nucleus, and that means a new isotope. When we're talking about a single element, and we're talking about different versions of a single element, we use the word isotope. But if we're talking about all the different isotopes of all the different elements, the more proper word to use is nuclide. Nuclide, you'll hear me using nuclide just as often as isotope. Treat them as meaning the same thing. So radioactivity was first observed in 1896 by a French scientist, Henri Becquerel, and he was looking at uranium salts that he actually inherited from his father when he was studying the process known as phosphorescence. And he noticed these particles would expose photographic paper even when kept in a closed drawer or dark paper. The radioactive particles still interacted with the photographic paper. And very soon after that, Pierre Curie and his wife, Marie Curie, they discovered the elements polonium and radium, and in fact named those elements. Polonium was named by Marie Curie for the fact that she was actually born and raised in Poland, so they named it polonium in her country's honor. She's usually associated with the French because she married the Frenchman Pierre Curie, but she was actually of Polish descent and was quite proud of her Polish heritage. The other atom they discovered that they're very well known for is radium, named for the fact that it produced these rays of radioactivity. In fact, Marie Curie was the one who coined the word radioactivity. So why are most atoms radioactive? Why do they undergo this radioactive decay? Well, first we have to look at what holds the nucleus together. And the nucleus is held together with a force known as the strong nuclear force. Now, you don't need to know the details of this, but the fact is protons and neutrons are held together very, very tightly in the nucleus. Even though the protons have a positive charge, and you're bringing lots of positive charges together, they would otherwise repel. But when you get close enough, the strong nuclear force becomes more powerful than the charge repulsion that we usually associate with two plus charges or more plus charges coming together. And the neutrons, which have no charge at all, still have the nuclear force. You can think of the neutrons as a sort of glue that can hold this nucleus together. And the bigger the nucleus, the more neutrons you need to hold all those protons together. And frequently, you will end up in situations where there are too few neutrons, or maybe even too many neutrons in the nucleus for it to be at its optimal stability. And as a result, the nucleus will decay from some less stable species to some more stable species during this conversion, during this release of some type of radioactive particle or some type of nuclear conversion. So the emitted particles may have a mass. Some do, some don't. They all have a certain amount of energy, and some are just energy, like the gamma particle, which we'll talk about later, and some have charges. We have particles that are positively charged, particles that are negatively charged, and particles that have no charge at all. All atomic isotopes with an atomic number greater than or equal to 83 are radioactive. That is, they are ultimately unstable. Now, some of them have very, very long stabilities before they release a particle, so they act as if they're completely stable. For instance, bismuth, which is atomic number 83, the most common forms of bismuth are all radioactive, but they take enormously long to decay, so they're essentially stable for all intents and purposes. So here's a periodic table. It's a very simplified periodic table. And the yellow boxes represent elements for which there are no stable isotopes. In other words, every isotope of any yellow labeled element on this periodic table is radioactive. And you'll see there are a lot of elements that are always radioactive. Every isotope of that element is radioactive. And you'll notice I've lightened the yellow for bismuth because while there are some very radioactive materials, the most common form, as I mentioned, of bismuth is radioactive technically, but it's so slow that it's not very dangerous to work with. And in fact, I have a chunk of bismuth in my home, and it's very pretty to look at, and it's completely harmless to me. Now, so in yellow are all the elements that are only radioactive. Their isotopes are only radioactive. In green are the ones that are named after scientists, and some of these scientists are very famous. LR is Lawrence. RF is Ernest Rutherford, who we've already talked about. Seaborg, Glenn Seaborg, SG, actually co-discovered 10 of the elements on the periodic table, all radioactive elements, and the last one was named in his honor while he was still alive. He's since passed away. MT, Meitnerium, named after Lisa Meitner, a German physicist who lived in Europe during the period of Nazi Germany. She was Jewish and treated very poorly and eventually escaped, but Lisa Meitner was the one who was able to explain the process known as nuclear fission, which we'll talk about at the end of this unit. Rankin, who we'll mention, is the discoverer of X-rays, RG. CN is for Copernicus, not a nuclear physicist, but a scientist nonetheless who studied the revolution of planets around our sun. Flerov, who ran a large nuclear facility in Russia, and that was taken over by Yuri Oganessian, OG, who is actually still alive. So he's the only one on the periodic table where there's an element named for him, and he's actually still alive. If we look down at the green on the very bottom, we have CM for Curie, for Madame Marie Curie and her husband Pierre Curie. ES is Einsteinium for Albert Einstein. FM, Fermium for Enrico Fermi. Mendeleev was the one who created one of the earliest periodic tables, so we have Mendelevium. and NO is Nobelium for Alfred Nobel, for whom the Nobel Prizes were named because he actually started them. A number of these elements are also named for places. I'm not going to go through all of them, but FR is France. PO, as I mentioned before, is Poland. So this is francium and polonium, named after countries that were related to the Curies. They discovered polonium. Their student, who was a French woman, named francium after France. We also have americium down at the bottom for America, and Berkeley, California, berkelium and californium. And just to remind you, whenever we're talking about radioactive elements, we usually associate one or two numbers with that isotope. The top number is the top number is the mass number, and the bottom number is the atomic number. These are whole numbers. The atomic number is just the number of protons, and that's how we organize the periodic table. The mass number is different for every isotope, for every nuclide. They each have their own mass number. So that's the sum of the protons and neutrons. So that gives you a rough idea of how heavy that particular isotope of radium in this case is. It has a mass of about 226 atomic mass units and 88 protons. And if we take the difference between those two numbers, we'll get the number of neutrons. So radioactivity comes in a couple different varieties. We have naturally occurring radioactivity, and 87 of the isotopes that are naturally occurring are in fact radioactive isotopes, otherwise known as radioisotopes or radionuclides. There are 339 naturally occurring isotopes of all types. 252 are stable. 34 of these long-lived radioactive ones that really behave like stable ones, but they are technically radioactive. And 53 are unstable radioactive isotopes, the ones that we really associate with radioactivity. There are isotopes that were formed before the solar system was even formed, so these are referred to as the primordial isotopes. Uranium-238 is an example of those, and you can usually tell these. They have enormously long lifetimes, what we call half-lives, which we'll talk about later. We also have isotopes that are radioactive because they're produced from other radioactive parent nuclides. Thorium-234 is an example of that. And we have isotopes that are produced every day because the Earth is bombarded constantly by particles known as cosmic rays. And these are mostly protons, mostly hydrogen-1 nuclei. So we're just talking about a single proton, sometimes more than a single proton. But most cosmic rays are just very fast, high-energy protons screaming down on the Earth, originated not only from other stars, but actually from other galaxies. And in fact, all the carbon-14 in the Earth today is formed from recent bombardment in the Earth's history by cosmic rays onto nitrogen-14, which is converted to carbon-14. We have synthetic radioisotopes, and in fact, even though there are only about 339 naturally occurring isotopes, there are about 3,000 that human beings have produced, and all of these are radioactive. So most of these 33, 39 known nuclides, everything, most of them have been made by humans. And these can be produced in big nuclear accelerators called cyclotrons or linear accelerators. They can be produced in nuclear reactors where atoms are split in a process we call fission, which again we'll talk about later. And some of them are isolated from the nuclear waste of these reactors because these atoms that are produced in the nuclear reactor continue to decay to other radioactive elements that may convert to other radioactive elements, eventually becoming stable isotopes. But in the meantime, they make plenty of different new what we call daughter isotopes or daughter nuclides, new radioactive material produced from the original radioactive material. And here we'll stop.